What if I told you there's an AI that can actually speak the language of chemistry? And I don't just mean understand it. I'm talking about creating with it, designing the actual building blocks for brand new medicines. Well, that's exactly the wild idea we're going to unpack today. So here's how we're going to break this down. First, we'll look at this huge roadblock in drug discovery. We're calling it the molecular language barrier. Then we'll meet the AI built to smash right through it. We'll see what it can understand, and then, the really cool part, what it can create. After that, we'll put it to the test and look at the actual numbers. And we'll wrap up with its most mind-blowing trick yet, planning out the entire recipe for making a new drug from scratch. All right, let's jump right in with that first big idea, the molecular language barrier. I mean, it really gets to a fundamental question, right? Why is it so ridiculously hard to design new medicines? At its core, it's basically a communication breakdown. Think about it. Molecules. They're the building blocks of medicine, right? They're like the letters, words, and sentences that can fight a disease. The problem is, they speak the super complex chemical language. And for us humans, learning that language, well, it's incredibly slow. That's a huge bottleneck for making new discoveries. So this language, it actually has an alphabet, and it's called SMILES. And yeah, that's an acronym. It stands for Simplified Molecular Input Line Entry System. All you really need to know is that it's a clever way to take a complicated three-dimensional molecule and just write it down as a simple line of text. Pretty neat, right? But here's the catch. Learning the alphabet is one thing. Actually becoming fluent, that's a whole different ballgame. And that, right there, is where our main character enters the story. An AI that truly speaks chemistry. So let's meet BioMedGPT-Mol. Okay, so what is this thing? Well, you can think of BioMedGPT-Mol as a new kind of large language model, like the ones that write poems or code. But here's the twist. Instead of training on the internet, it was fed a steady diet of chemistry. It's been custom built to be an AI research assistant that is totally fluent in the language of molecules. It's designed specifically to fix that communication problem we were just talking about. So how did it get so smart? One word, scale. We're talking about a mind-boggling 5.8 million question and answer pairs that it was fine-tuned on, every single one of them about molecular science. It's like it went through the most intense, turbocharged PhD program you can possibly imagine, just soaking up millions of examples until it became a true expert. Okay, so we've got this expert on our hands, but what can it actually do? Let's start with its first major skill, just plain understanding molecules. For this part, think of the AI as a brilliant translator and a super sharp analyst. And this isn't just one thing, it's actually a whole toolkit. For starters, it can do what's called name conversion. That just means it can translate between all the different ways chemists write down a molecule's name, like the super formal IUPAC name and that SMILES text we mentioned. Then there's molecule captioning. This is really cool. It can look at a molecule and spit out a detailed, easy-to-read description of what it is and what it does. And finally, and this is a big one, property prediction. It can look at a molecule and estimate things like, is this likely to be a good drug? Or how toxic might this be? The really crucial stuff. But okay, understanding is just half the battle, right? The AI's second skill is where things get really exciting. We're talking about creating new molecules. This is where it goes from being just an analyst to being a creative inventor. And just like before, this breaks down into a few key abilities. It can predict what will happen when you mix certain chemicals together, a huge time saver. It can also do something called molecule editing, which is exactly what it sounds like. You can give it a molecule and just tell it, in plain text, how to change it. But the most powerful tool in this kit is property optimization. This is where it doesn't just change a molecule randomly, it edits it with a specific goal in mind. Like, hey, make this a better drug. And this is where it gets super practical. You can literally just ask it a question like you would a human colleague. Something like, hey, can we tweak this molecule to make it more drug-like? And here's a perfect example of what happens next. On the left, we've got the original molecule, shown as one of those SMIL strings. The AI was asked to improve its drug-likeness score. And on the right, that's the AI's answer, a new optimized version. Now, it might look like a small change in the text, but in chemistry, that's a huge deal. So the big question is, how did it know what to do? Well, this is the part that blows my mind. It can actually explain its thought process. This quote is basically a summary of its reasoning. It looks at the original molecule and says, okay, this little part right here, this group, It's hurting the molecule's drug-like properties. And then it lays out its plan. So I'm going to replace that part with something better, but I'll make the change as small as possible so I don't mess up the rest of the molecule. This isn't just random guessing. This is targeted, intelligent design. Okay, so all of that sounds really impressive, right? But talk is cheap. How well does it actually perform when you put it to the test? Let's dig into the data. What's so cool here is that we get a direct head-to-head comparison. Take a look at name conversion. BioMedGPT-Mol is hitting 77.1% accuracy. That's a solid 7 points higher than the last best model. But check out molecule editing. The difference there is huge. We're talking nearly 75% success versus just over 54%. That's a massive improvement. And even on that super complex multi-property task, it still squeaks out a win. This chart really spells it out, doesn't it? When it comes to optimizing for just a single property, BioMedGPT-Mol is at the top with a 77.2% success rate. And look what's really interesting. It's not just beating other specialized chemistry AIs. It's also outperforming a massive general-purpose model like GPT-4 Turbo. This really shows that for certain jobs, being a specialist pays off big time. But for me, this is the number that really pops. Over 95%. That's its success rate when you ask it to juggle multiple goals at the same time. And that's how it works in the real world, right? You never just want one thing. You need a drug that's better at being absorbed and less toxic. It's a complex balancing act, and this AI is nailing it almost every single time. And get this, it's got another gear. The model has this special mode for explicit reasoning, where you basically ask it to show its work, to think out loud like we saw earlier. And when you flip that switch on for the tricky tasks, like molecule editing, its performance actually jumps up to 79%. It's almost like the more you force it to think step by step, the smarter it gets. Okay, so this ability to think like a chemist is a huge deal. It's not just shuffling letters in a text string anymore. And that leads us to its most ambitious skill yet, moving beyond just generating a molecule to actually planning out how to make it. We're talking about the future drug blueprint. This brings us to what's pretty much the final boss of organic chemistry, retrosynthetic planning. The best way to think about it is with a baking analogy. Imagine someone hands you a perfect finished cake. Your job is to work backwards from that cake to write the exact recipe, step by step, all the way down to the basic ingredients you can buy at the grocery store. For a chemist, that means taking a finished drug and figuring out the entire chain of reactions needed to build it from simple, off-the-shelf chemicals. It's incredibly hard. So how on earth do you teach an AI to do something that complex? Well, the researchers used a really smart three-step approach. First, they just got the model used to the idea of multi-step planning. Then they taught it how to think about its plan, using that chain of thought method again. And for the final step, they fine-tuned the training to really focus on one thing, getting the final answer, that chemical recipe. Absolutely perfect. And the results? Honestly, they're pretty stunning. On the industry standard test for this, which is called RetroBench, it scored a 39.1% accuracy. Now, I know what you're thinking. 39% doesn't sound amazing. But in this field, that is a huge number. It means this smaller, more efficient model is competing neck and neck with massive, super expensive models like GPT-4 on one of the hardest tasks out there. It's totally punching above its weight. And all of this leaves us with one big, fascinating question to chew on. You know, for hundreds of years, discovering new medicines has been a uniquely human thing, a mix of genius, intuition, and a whole lot of trial and error. But now it looks like we have a new kind of partner at the lab bench. So you have to wonder, how long will it be until the next big life-saving drug is designed not just by a person, but by a human working hand in hand with an AI that truly speaks the language of molecules?